I want to give a little bit of an overview of what I call the mechanistic trait-based approach. And it's, I guess, a summary of what we have been developing at the Center for the Ocean Life in the last 10 years or so. And I'll actually do it as playing 3 acts. So the first act is what is actually the trait-based approach that will start the main character here, which is trait distribution. Then I'll go on and talk about what are actually traits, and last act is about trait-based modeling. And there we go. So the first one here is, what is a trait-based approach, at least in my mind? And if I should try to put it in one sentence, for me, it's about trying to describe the structure and function of entire community. That's a lot of what we do in ecology, but here I want to do it from a small set of traits of individual organisms. And the way to do that, and the way to describe the structure and function of a community, is really with the trait distribution. And for me, that is the key in what we want to do. So I'll spend a little time on that. So it's very simple in a sense. The trait distribution is just the biomass or the abundance of organisms, all organisms, as a function of the traits. And the central things we do here, which is different from a lot of other ecology, is we throw out the concept of the species. We don't care about which species the individuals are from. We just care about the traits that we select. And it can, of course, be multidimensional, will often be, but it gets difficult the higher dimensions. So therefore, we want to keep the dimensionality down. And I'll just give a few examples of mainly measured trait distributions here. So the main trait we often talk about is size. And I just want to put up this paper from a recent, or figure from a recent paper by Hatten, where they looked at the size distribution of everything, but bacteria from whales, but actually not just in one community, but in the entire ocean. I mean, the entire global ocean, which is a massive effort. And of course, that's a little bit of an odd thing to do because the entire globe is not a community. But in the appendix, I have a lot of so the same distributions here for different places in the ocean. That's something that's been done a lot with the size distribution, but we want to go a little further. And here, take another one from Kasia Kinic, which is a work that we did together. And here she has on top of it, that's a trait distribution of microbes from protists, bacteria, and mesoplankton in the California current. And then she looked at different places, so the upwelling region down to the oligotrophic gyre. We see we have roughly the same kind of structure, but different biomasses evidently in the different productive regions. But she went one step further and looked into the trait distribution and looked at other traits. So among the unicellular organisms, she looked at traits related to resource harvesting, mainly whether they were autotrophic and heterotrophic. Among the multicellular, she looked at activity traits. I mean, are they essentially passive feeders or are they active feeders? But in all of this is integrated into the fraction of the biomass. So it's really the full trait distribution that you have here. Here's another example from my own work about fish. So these are measured trace distribution. With fish, it's a bit harder to talk about size because a fish can be almost any size. You're more talking about the trait that you're looking at is the maximum size. So here we have the biomass of fish from different species in different asymptotic size classes. So the points here are measurements, the other ones are various attempts at theoretical explanations. And you have the same here. So here you actually have resolved both individual size and asymptotic size. So this would be the biomass of species, which are small at the asymptotic size. Here we have the biomasses of species, which are large. So they are both trait distributions. Here's another attempt that is by Philip Brun, a former PhD student at the center. He looked at zooplankton and he looked at the average length across the global ocean. This is actually not a bona fide trait distribution as such, because he's not looking at the biomass here. He's just looking at what are the average length of species, which are different places around the Earth. ideally, you would like to go to the next step and get the biomasses, but it's actually hard typically to get both places. So sometimes you're just going half the step towards the trait distribution. So looking at trait distributions here, you're immediately faced with the next question: what are actually the traits that you're using for the trait distribution? And here I will introduce the trait purge, because what we often see is big lists of this and that organism group where there are these and these and these and these traits and that, there are all these traits. There are many traits that describe a given organism or a given group of organisms. That's not the hard part. The hard part is figure out which are the traits that we want to spend our energy on, finding trade-offs related to that and resolving the trait distributions. And that's a subjective selection process, and we had a discussion about that already this afternoon. And there are two principles here. One is you want a trait that's taxa-transcending, so something that's described as broad a group of organisms as possible. And I already mentioned size, which of course is a great starting point. And then it should be concrete. So it should be something that you can relate to something measurable. For instance, something related to a functional response, size, density, other kind of things that's concrete. Traits like effect response traits, that's also been talked about, are actually not very useful, at least not in this context, because they're not concrete. What is an effect and response trait? It's not something we can really measure. We also often talk about species which are R or K strategists. That's also hard to use as a trait because it's not concrete, it's not tied down to measurable traits. So what we need is a prioritized list of traits, and preferable traits which are also orthogonal in the sense that they are not correlated. So we want to take that correlation out of them. So I here have a modest suggestion for a list for unicellular organisms. I would say the main trait here would be cell size, mass or volume, depends on the application, what's most convenient. When you go to the second level, it gets a little harder. I mean, one way is to say, well, it's investment in organs. It could be the investment in mitochondria, chloroplast, and so on, the ones that relate to resource harvesting. Another central trait when we talk about plankton and phytoplankton in particular is the vacuole, because that's a central trait of diatoms, which are a very important strategy. So whether one would want to focus on the other as the main trait, I'm a little divided here. Next, I would say, again, related to resource harvesting, mixotrophy comes up here high on the list, and you can think about others. When we talk about multicellular organisms, so I'm not just thinking about plankton here, but any kind of multicellular organism. It's harder to talk about size, as I said before, because they change size during life. It's almost a state, the size of an organism. But what is the main trait is the adult or the asymptotic mass. And then when we go next, again, I'm a little divided. So there's one trait that we have not talking too much about, which is actually key for the fitness of organisms, which is the adult offspring size, the ratio between that. And that's because we can say there are two groups of organisms. There are those that have roughly an adult offspring size of 1 to 100. And then there are those which within the group have a constant offspring size, which means that the adult offspring size is increasing here. That's taken from a recent work by Rémi Denessier, who is here today. And the reason why it's so important is that it actually matters enormously for the population growth rate, which is the fitness. But the other important trait is the somatic growth rates. I mean, are you fast-growing species or slow-growing species? That, of course, correlates with a lot of other traits. The resource uptake rate, your maximum growth rate, probably also your the basal metabolism, etc. But it's something that encompasses that whole dimension, the pace of life dimension. Further down, I mean, I would say something related to reserves or seasonal strategy, in particular in high latitude environments, prey preference, habitat selection. For instance, are you high or low in the water column comes up here. I don't think that this is a discussion that we need to have. And of course, it also depends on the application, what you choose here. Okay, so once we have decided upon the traits, the next will be to do a trait-based model. And to illustrate what is the concept of the trait-based model here, we have seen several already today, but here I go a little bit more abstract. I'll actually start up with a model that's not trait-based. So this is a standard model. All models start essentially with individual-based rates and the parameters of the fundamental processes. And what we are doing is calculating the population growth rates based on these processes in a given environment. So I could write that here as a functional response minus losses. And once you can do that, you can put it into an equation and solve for the population biomass, make that feedback on the environment, and you have the loop and you can solve that. That's fine. That's what we always do in a simple population model. But when we want to go to the community, we are facing the problem that we have defined a food web, and we have to find a food web of populations of specific species, each with different parameters that we need to define. And it works pretty well, such type of food web models, but they are hard they're not very portable. If I set up a food web model for a certain region, I cannot put it into another region because that other region will have different species with different parameters, etc. Trait-based models are essentially the same. The core is exactly the same here. We have processes that are affected by the environment, but what we have is the abstract layer of the traits that we have selected. And the trick here is then to say, well, given these traits, I need to be able to specify all the parameters of the processes here, and perhaps how these associations are determined by the environment, which means that any kind of organism with a given certain trait combination will have a certain set of parameters. That means that my population growth rate now becomes a function of the traits in the environment. It's the same game I'm playing, just as usual, except that I have the traits in here, so it gets a little bit of more complicated object. But what I gain by that complication of the traits is that I can now scale directly to the community, which is a trait distribution, and doing it by exactly the same models that we usually do to go to the population level. But I can sidestep that whole complicated food web and go to the trait distribution. And that's, well, essentially the idea of what I say a trait-based model. So I give some examples here. The first is more of a conceptual example. Wait for it to shift here. It's somehow slow. Okay, here we go. So it's about mixotrophy. It's an idea by Johan Brueggemann that we developed in a recent paper here. And it's just when we think about the trait of resource harvesting of a phototroph or mixotroph, that can be anything between fully phototrophic and fully mixotrophic and everything in between. And if you say that's just the investment that it can make, it's essentially just one trait, which is how it is on that spectrum here. And then we can write simply the population growth rate as simply the minimum of how it acquires its resources. We can solve for the trait distribution as that, put in its effects on the environment, and we get something like this here. So we have starting, this is in a model chemostat setup here. I have time. I start with a trait distribution here, and as time goes, the trait distribution evolves, and we have the biomass of the different morphs here, and we can even calculate the optimal, but I won't go there today. So this is essentially the concepts, and the trait-based models we have seen today all follow conceptually this route. I want to take an example here from plant ecology because it's actually one of my favorites, and I think one I'm striving towards achieving also with the work I do. It's a work by Daniel Forster, and they have what he said. He had two traits here. He used plant height as the main trait, and the other one was the leaf mass per area, which is a central trait in resource harvesting for plants. So I am not going into the details, but just what came out of it. So here he's showing the environment. So that's the productivity and the disturbance, which was matters for plants. And then you can look at different, and here you have the two traits and different examples of different places in the trait space here. And each of these examples then leads to, here as you go to time, to a certain climax population or community here with different diversity of traits and typically different structure. So, and these essentially are the trait distribution that we want to calculate. Another example is from our own work in the center. That's work by Camilla Serra-Pompei, who made models of zooplankton, in particular copepods, again with two traits. It's very similar in a sense conceptually. The main trait was adult size, which corresponds to the plant height. The other one was a measure of the pace of life, just discretized into either are you an ambush feeder, so slow growing typically, or an active feeder, which is fast growing but with a higher risk. And here, what she did was go into the trait distribution. So what we see here, we have body size here, and then the unicellular organisms here. And here we have different populations of the passive copepods and the active copepods. In eutrophic environment, we generally have higher population levels, and we have many more, in particular of the active and larger of the active copepods. And that general concept you can put in a global model and look at the global distribution. And I'm just waiting for the slides to change here. Maybe it will come. There it is. So you have the copepod biomass distribution. Again, you can look at the structure, different places on the globe. So summing up here, I mean, if I think of the trait-based approach here, what I've been talking about a lot here is the models. That's because that's what I'm doing myself. But I think the trait-based approach is much more than just models. It's also a way of integrating experimental work of individual organisms, because you direct the experiments towards not so much chemostat work, but really trying to understand the physiology of the individual. It's also statistical analysis, so meta-analysis, like the word Kyle Edwards are doing a lot, or even theory to understand the individual organism. And it's also another bit of work which is trying to make empirical trait distribution based on the data that we already have. We're not seeing so much of this in these meetings, but I think it's a very important approach as well. And for me, the trait-based approach is when all of these things are playing together. So in the final act here, the mechanistic approach to trait-based ecology, the star here is really the trait distribution. But I would want to finish off by saying I don't think this here is the end to what we're doing when we're doing ecology or marine ecology. There are many other approaches. We have the population ecology, community ecology, macroecology, evolutionary ecology. And trait-based ecology takes a lot of things from all of these approaches here and brings them together. But it's not an end to meet all our needs. If we, for instance, want to study a very particular region or very particular species, well, that trait-based approach may not really fit the bill. We may want to make a food web with specific species because that's what we want to have the questions about. However, when we want to look at the global scale populations and global scale life, and particular global scale life in the future, that coarse grain descriptions where we throw out the idea of the species and just look broadly at the trait distributions is a very powerful approach. So with that, I'll just say thanks for your attention, and I'm happy to take questions.
Questions? Are there any online? Looks like no. I had a question, Ken. I like the hierarchical structuring of the traits and the kind of definition, but I mean, it was just for my edification. I was curious why you excluded R and K selection as a trait. Is that just because it was comprised of multiple traits, or
Because I cannot, it's hard for me to say what should I measure if a species is R and K. I would say that's rather something that come out of an analysis of a lot of different traits, and maybe even in a specific context, whether it's an R or K selected one. So it's not very concrete as a trait. It's like I would much rather like a trait which is concrete. Say I can measure the clearance rate, or I can measure the investment in chloroplast. Oh, that's easier to work with.
Yeah. Any others?
It seems like most of the traits that are presented are continuous. What about presence, absence, or categorical traits, and how do you view them in this scale?
Yeah, I think definitely categorical traits, and you would actually like, if possible, to have traits to be categorical, because that's easier and model-wise, because you don't need the continuous trait. I mean, one I described there was with the cone pots, where instead of having a continuous growth rate axis, just saying, well, they're active and passive. That's one of taking it into two different categories. Another one, which is obviously for a categorical trait, would be the degree of jelliness. If you look at the density of zooplankton organisms, you see that they actually group in two groups. They're either those which are dense, or they're the jellies. And there's not that much in between. To work with a categorical trait, I mean, jelly or not jelly. There are probably others, but I cannot right on top of my head come on decide one they are.
Okay, there's a question online from Jonas.
Yeah, hi. Thanks for a great talk. So I'm a bit curious about what one of the sort of things you said. I was not part of the important trait discussion, so maybe you already went over this, but you had like size as one of the most important traits, and then you had a pace of life or growth rate as one of them. And I thought these were sort of quite tightly intertwined. So sort of what aspects of these two things do you think are orthogonal and important to sort of
good question. Of course, I mean, the pace of life and size are strongly correlated. I mean, small organisms, they have a shorter lifespan than larger organisms. When I think about pace of life, I would think about it size correctly. So if I, for instance, were to look at growth rates of organisms as a function of size, well, you'll get that kind of typical metabolic type of scaling, but you'll also see a lot of variance across. So that other axis would be essentially that variance across. I would say, well, that would be the other trait, and I would use as the main thing something that characterizes that. That would be the clearance rate or maximum growth rates or something like that, and consider a lot of the other things as being correlated to that.
All right, thanks.
It's also related to an important part, which is defense. I mean, if you're a fast grower, you also typically expose yourself more for risk and are less defended, whereas more defended organisms, they expose themselves to lower risk.
I have a question. We've now heard throughout the day about the importance of adaptation, the evolutionary responses, as well as dispersal for sort of setting the stage for especially future sort of communities. And you had sort of a last comment about how you are arguing that these trait-based approaches are really powerful for understanding sort of how our marine ecosystems are going to respond to climate change.
Yeah, thanks for that.
Okay.
Thanks for that question, because I was actually thinking about it during the day here, and my thought was, why do we actually think that phytoplankton or plankton at all would adapt under climate change? I mean, it's clear that if I take an organism and put it into a chemostat and change the environment, the carbon dioxide or the light or the temperature, it will eventually adapt. But if I look out there are all kinds of species, and within each species there are many, many different strains. So I can imagine that all kinds of traits, so to speak, also temperature-wise, are already out there. So I see that the climate change would just be a question of winners and losers among the strains that are already there, much rather than it will be about evolution. Perhaps there'll be evolution at the ends of things, in the warm side of things, because you'll have species that need to be even warmer tolerance. But for the rest, I'm not so sure that the evolution part is a key to understand it. It would just be saying that it's a biodiversity is already there that would deal with it. Maybe that's a controversial statement. I don't know.
Okay, David.
Thank you. I really enjoyed that. Thank you. I was curious in your question about or your comment about there being a lack of data databases. Do you have any thoughts on why it might be that we as a community are lacking that, and what we could do differently, how we could modify to solve that issue?
Well, I think we have some way we have databases, and we are beginning to acquire databases of the traits, which is definitely a good start. But the hard part is the biomass and making these trait distributions, for instance, over space, because we need a lot of measurements, and much of it we don't have. But I think what the way to do it is to build on top of the quite advanced statistical tools that are coming about species distribution models, and just translating that using the trait-to-trait distribution models. Perhaps it becomes even simpler because we need data about fewer species to do the trait distribution models. But I see that as a way forward. I hope that answers your question.
Yeah, I think
Comment on it. I saw a comment come up. Okay. Are there any further questions? Okay. Well, I want to thank Ken again.